agenda. Hopefully you've all come and enjoyed the refreshments, beer and pizza, and soft drinks, courtesy of Discus. I'm going to hear from Discus a little bit later. I'm going to do a quick introduction. We're going to have a chat from someone who's part of this event space, and then we're going to launch into a couple of talks for tonight. Just a quick warning that the event is being recorded, so there might be photos and bits of film content going around, and it's also live streamed. If for whatever reason you don't want to be included in the footage, that's absolutely fine. Just let me know and I can make sure that you are not in it. And before I give a bit of a welcome about Silicon Brighton and the event, we're going to hear from Andy, who works for Eagle Labs, which is this fabulous space that we're in this evening.
Lovely, thanks, Grace. So welcome, guys. Welcome to Barclays Eagle Labs. Just want to give a bit of a background and a bit of a housekeeping bit that I have to do before we start. If you need the toilet, it's through the door, big sign toilet, down the stairs, follow it round, and they're on the left-hand side. There should be no fire alarm going off this evening. If it does, just follow me. I should be out that door first, over to the pub, and we stay there. All right, so that's the best thing to do. Just a little bit about Eagle Labs, so we are here. We are a business incubator. So we love to help and support businesses grow and scale. So whether you're looking for some mentoring, you want to join one of our fabulous business incubators that we've got running at the moment, get in contact with me. They are different and wide variety of programs. So if you're looking for funding, we're able to do a funding readiness program. All of these courses are free. The mentoring is free, so fill your boots. If it's what you want to do, you want to grow your business, speak to me. Let's see where we can go. I'll hand you back to Grace. Have a great evening.
Thank you, Andy. Eagle Labs is dog friendly, and I've brought my dog up because it's easier than laying him wide at the back of the room. I'm so sorry about that. Trying furiously to pretend that nothing is happening. So yeah, just a little bit of an intro about Silicon Brighton. We support Sussex Data Science Meetup. But actually, we support lots of different meetup groups that happen across the city. There are, in fact, 30 actually groups or so, all sort of across, and he's still whining, all across sort of digital and tech expertise, really representative of all the kind of skill sets and industries across Brighton. So check out all the different ones. They are free to join. Much like this one. They're all available to people of all levels. So if you are a student, you're just starting out in your career, you're thinking about career switching, perhaps you have a particular job or specialism or expertise, but you're trying to think a little bit about maybe learning about something different, everyone is welcome. And all the talks are hybrid as well. So there are people probably dialing in online tonight as well as in person. And the idea behind all of this is it's just to make the industry and the events themselves as accessible as possible. These are all of our supporters. So the way that we allow these events to be free is through the businesses that contribute to us financially on a monthly basis. So a massive, massive thank you to all of the companies that do that. And if you are a leader in a business or work for a business that you think might benefit from the supporting Silicon Brighton, then let me know, come and have a chat, or speak to someone and tell them about the great work that we're doing. These are our values. So every venue that we work with, every partner we have, every meetup that we support, and all of the attendees, we really sort of expect people to uphold these. If for whatever reason you feel that that isn't the case, then again, always come and speak to me, because we absolutely stand by these. You can follow us on socials. So it's amazing to get together in person, but we've got a really strong online community outside of the in-person bit as well. We're on, I don't even know if I'm supposed to say Twitter, but X, TikTok, Instagram, and LinkedIn as well. So follow us online. And also join our Slack community. So there's a really avid community of sort of 3,000 or so techies, again, all at different levels, all on there for different reasons, all continuing the conversation in between these events. So feel free to join us on Slack as well. And just on the subject of all things data, Earl conference, which some of you might be familiar with, but it was previously just for R coding, but it's now for R and Python. It's actually coming from London to Brighton for the first time this year. We'll be supporting it, and it's also being run by Dataco, so a local data business who are also partners with running a number of the meetups in Brighton. They're actually taking submissions for abstracts at the moment as well. So check out the website, get yourself tickets, think about maybe speaking or getting involved in some way. We'd love to see some of you at that conference in September. Really exciting that it's coming to Brighton. And just to give you a bit of an idea of the breadth of the events that we host, we've got Brighton R coming up on the 22nd of February. There's People and Culture Club also that day, that evening. That's more of a drink, and Brighton R, there will be talks much like this one. We've got Women in Blockchain talks coming up on the 27th of February, so all things blockchain, and not just for women or people who identify as women, it's everyone welcome. And then Tech Jumpstart as well on the 28th of February. Again, all of these events are available to people at all levels, but Tech Jumpstart is very specifically for people maybe thinking about getting into the industry or a little bit newer, maybe if you don't sort of feel comfortable coming to some of the more established meetups. Join the group if you haven't already. Join Sussex Data Science. You'll get notified about all the events coming up, and their SEO is bang on, so you'll start getting notified about all the other groups as well that are happening, or simply check out Silicon Brighton. I'm now going to hand you over to Chloe, who works for Discus, who are also supporting and running this event. Couldn't have made it all happen without them. So step up, Chloe. Thank you.
Thanks very much, Grace, for that lovely introduction. So hi, I'm Chloe. I'm a research fellow working at Discus, and we're an interdisciplinary research centre where we're trying to kind of connect research that happens at the University of Sussex, and particularly focusing on data science, and connect it to external organisations, and particularly trying to apply it to kind of real world problems. Mostly we collaborate with external organisations and also people from different departments in Sussex. And we also host industry and student networking events, trying to connect the local data science sector with our kind of really good data science students that we have. And also trying to facilitate knowledge sharing with events like the Sussex Data Science Meetup. And if you want to hear about any of the latest Discus updates, you can follow us on LinkedIn, which you should get to through that QR code there. And now for the bit you've all been waiting for, we'll move on to our talks. So first up, we have Luke Berthouse. Do you want to come do your wizardry, Luke? So Luke is a professor at the University of Sussex, and will be talking to us about a neuroscientific perspective on large-scale comms networks. There'll be time for 5 minutes of questions at the end of his talk. Over to you.
Thank you. All right, well, it's a pleasure to be here. I've not been very good at attending these meetings in person, but I did attend a few online, so I have a sense of how that works. And what I want to do is to talk a little bit to you about work that we have been doing over the last 5 years, and which I think is providing a very interesting ground for people involved in data science and developing techniques. So this figure, this picture here is not mine, obviously. I'm sure you get a sense that it must have been AI generated, and it was. And the prompt was that I wanted to convey this idea that we might want to look at communication networks. And now when I say communication networks, I should be actually more general than that, and basically say any kind of large-scale deployment. So that could also be distributed software systems. I will talk a bit about that. And this idea that we might want to model or think of them, as the kind of complex systems that the brain is. So that was the prompt. So to maybe get you started on this, think about what's happening right now, how this meeting is happening. So obviously we're in person, which is very nice, but actually a lot of what's happening here is underpinned by a lot of network stuff, right? So for example, my computer is connected to that, and some people are online. Some people might probably be consulting their phone at some point during the talk. So there's a lot of network infrastructure which underpins pretty much everything that we do, okay? And so obviously the people who manage that, so network operators, have an interest in trying to keep things to operate. So that gave rise around 2016 to this notion of AI ops. Okay, so AI for IT operations. And basically it's about developing AI tools to get a sense, a real-time understanding of what's happening on your network. And here, to be clear, just to scope this correctly, I'm not going to talk about traffic engineering. I'm not going to talk about network optimization in the sense of how do you improve bandwidth and all that. I'm rather going to be talking about the people who are interested in monitoring what's happening on the network with the view to do essentially two things. One, detect anomalies or predict failures, and should a failure occur, which is typically very costly, do something called root cause analysis, find out how that came about. All right, so these are the two aims. And what I'm going to show to you is that this is made fairly difficult by a number of challenges. So one which are called the infrastructure level, which is that if you think about networks a long time ago, they were pretty easy things to understand. Okay, so you might have switch routers and a few machines, and things were very clear. But today it's very different. Okay, so these structures are no longer static or predictable physical systems, but they might be people call that software-defined resources that are going to change and reconfigure on the fly. The networks. So if you think of a bank has to update its spark continuously. What it cannot do is just stop its business, change the network, and then put a new version on. So it has to update continuously. And that leads to a system that basically has legacy, quantities on the system as well as new ones. So you end up with a very large, very complex heterogeneous network. And then, of course, we are users and we want more and more from these networks. So we're trying to do more and more complicated things, and software developers oblige, and they create these incredible things like Netflix and, in China, Alibaba and Alipay and all of this. So you have services that are distributed and that are continuously changing under all of the, the need that we have. And of course, in the same way as these networks are no longer very static and easy to handle, software have also gone away from the monolithic approach or having a nice little bit of software to things like microservices, okay, where you have both what we call horizontal and vertical scaling. All right, so that's already a problem. That sounds a bit difficult already. And then you have issues at activity level, by which I mean, if you're a network operator, you need to monitor things on the network. And the question is, what are you going to monitor? And here, in a way, how you conceptualize your network, how you think of how things work on the network is going to have an impact on what you collect, when you collect it, and for example, with which sampling rate, okay? And what we find is that, yes, these networks collect a huge amount of events, but sometimes when you look at node level, you don't actually get a lot of events. Now, I want to be clear again, I'm not talking about packets flowing in the networks here. I'm talking about your router sending a message saying, I'm okay, or this happened to me. I'm talking about this kind of network monitoring events. And when you look at the log events, what you find is that actually there's a very low signal noise ratio. And most of the time, the signals that, the events that are given or recorded have actually no actionable meaning. They're just there, okay? And that, of course, if you think about the amount of garbage that you get, by which I mean, technical word to say that, garbage in, garbage out, your data is made up of a lot of garbage, essentially, okay? Just to add to the nice things here, you will find that event labels might not be reliable. So it's not that people have very specific standardized approach of recording what happened on the network. It can be very ad hoc. So it's very difficult to look at events, parse them, and understand what they meant. I'm talking about very large scale networks here. So, hundreds of thousands of machines. So that's a lot of events, okay? And then other little details like the timestamps of events, which can depend on how these events are recorded. So sometimes you have polling devices, which it's not that the event occurred at the time it's recorded. The time that you are given is the time at which the data is being transmitted, for example. And then finally, and I'm done with how complex it is, but I think it's enough, is actually in relation to failures, the heterogeneity in the mechanisms that produce the signal that tells you there's a failure. So if you think about it, it could be that the signal, the device itself is telling you something wrong is happening with me. But if that device is shutting down, for example, that device cannot tell you that it has shut down. So maybe you are just going to see the follow-up impact of that device no longer answering to polling requests, for example, right? So basically, as someone who did not have a background in computer networks, but did think of other kind of complex systems, namely the brain, it became increasingly apparent that we were looking at something fairly similar. In fact, it shares a lot of very similar properties, so which I'm going to try to highlight here. And you will be disappointed to know that these colors are not actual colors, so your brain is not looking anywhere that nice, but I'm sure it is very nice, but not that nice. So on your left, you have a representation of some data center of Facebook. That's just a tiny bit, of course, okay? But what I want you to see is some kind of similarities in the fact that you are dealing with multiple layers. And if you know anything about Cortex, you know that you have multiple layers, of course, and then structured layers. It's not like, neural systems are completely vanilla structures. They have some structure. Very importantly, as in brain, we have changing networks. We are developing, we are learning. All of these things impact your network. And of course, changing networking, computer networks happen because people have to renew the hardware, okay? Changing services. Now you might say, what are the services in the brain? Well, think of the computations that your brain are doing, and of course, these are changing, okay? And of course, multiple time scales. So again, if you think about development, okay, or learning, these are two changes in the system that occur over very different time scale, right? We are still developing, we are still learning, okay? And so it's a little bit the same. And of course, you have the fastest time scale, which is that none of these systems are closed systems, right? They are subject to outside interference. Of course, for a network operator, that's going to be user demand, right? So suddenly everybody wants to look at their Netflix. In your brain, that could be that you suddenly have a very strong input. So I hope to convince you the intuition why these two things are kind of similar. And there is one more thing which I will get to, so maybe I'm not going to mention it, but the key thing here is that in both cases, think of it as you have a system where you have a dynamics that operate on the network, and you have the dynamics of the network, okay? The network is changing, and of course you have a dynamics on the network as well. And this interaction has been something that, of course, has interested neuroscientists for a very long time. So the question was, well, how do neuroscientists try to understand, or how do you get insights into how the brain is working? And of course, brain connectomics has been the subject of a lot of research over, say, since 2000, the early noughties, really. And people have been looking at different forms of connectivity, not surprisingly. So of course, on the one hand, you have your structural connectivity, which is basically your cabling, right? So I don't think I need to explain that very much. But of course, this is just the structure. This is the cable. And for sure, you cannot expect your brain to be fully explained by understanding what the cables are, right? You need to know how these things work. Right. So then what people have been looking for are things like effective or causal connectivity, where now you are more thinking in terms of, are there causal interactions over my system? And of course, if you're thinking in terms of a network operator, that's the kind of connectivity that you would like to understand, right? Causal relationship in your system. Why? Because if you have a failure, you might want to be able to say, okay, this is happening because of the interaction between these two components, right? In brain, of course, there are paradigms, and which I'm happy to talk about later. But typically, you're going to find that it relies on two things. First, it's often at the level of macroscopic areas of the brain. Okay, so it's very rare that you do causality at the level of single neurons. And the second thing is it's often based on some idea of perturbing the system and seeing a response, right? So you want to maybe give an input and then see how that, how that impacts the rest of the system. But you won't be surprised to hear that banks are very reluctant for people like us to say, how about we disconnect this, or how about we change the bandwidth here and see what happens? For reasons that I ignore, they don't like it. So what people have done really is looked at a halfway house, if you like, which is this notion of functional connectivity, which really is about statistical dependencies between nodes. Right? So in this little cartoon, you see that on the one hand, you might have some knowledge about the structure, okay, the connectivity between your nodes. Ideally, you would want to know effective connectivity, which will be saying, for example, directed connectivity, directed links, or even weighted links between your nodes. But functional connectivity is kind of just going to say, well, you appear to have some statistical dependence between these nodes. And now you're thinking, well, surely this functional connectivity must depend on structural connectivity. And yes, it does. But the point is, and this is maybe the issue with current management of network operators, is that they rely almost exclusively on the understanding of the physical connectivity. But what we know from brain is actually, yes, physical connectivity helps, but does not predict very well what's going to happen at the level of activity. And a very good example is the way people used to do surgery for epilepsy, for example, where you will try to identify the spot, right? But now we know that actually removing the spot does not necessarily remove the epilepsy. Why? Because it's a dynamic process and it's often a network disease where actually it's the nodes around the disease point that generate the epileptic seizure. Okay, so what we have tried to do is to introduce this notion of functional connectivity in network management. And how did we do that? Well, we thought, if you think about a single spike of a single neuron in a brain, it has some of the properties that I've discussed so far. It's very unreliable. Okay, I'm not going to get into the detail, but if you know a little bit about neuroscience, you will know that same stimulus doesn't give the same spike train. It's therefore poorly labeled. The timestamps are pretty random. So it has a lot of, and also there's no semantic attached to it, really, right? That spike doesn't tell you I'm the face, I'm doing that. It's just a spike, right? So what we decided to do was, in order to get rid of all of the issues with reliability of labels, is ignore all the messages themselves, but just purely rely on the timing of the events. That's it. All we're interested in is an event occurred. We're not interested in whether that event is saying, I'm a failure or I'm okay. We'll just say, take the event time, that's it. And basically, that means that what we mean here by functional connectivity is, that we have some, that nodes will be statistically dependent if they are maybe involved in the same kind of, providing a particular service, or maybe are involved in a particular failure. Okay, so in the interest of time, what I'm going to do now is maybe go a little bit fast on the technical aspect of how we solve the problem, not entirely, don't worry, but I'm going to tell you then how we have formulated this into a data science problem. So the first one was that if you're a new scientist, the way you look at statistical dependence might be things like mutual information, coherence, or of correlation. This doesn't work for what we have here for reasons, for example, of the sparsity that I mentioned, that at node level you have so few events that you might be, for example, having one event every hour, whereas another node might have a lot of events. And that just makes, if you know a bit about correlations, that just doesn't make very robust estimate of correlations. Coherence has the same issue. Mutual information is problematic in terms of scale. Okay, so what we did was, in collaboration with Nikos Georgiou from the maths department, we came up with a new statistic. Now, this is looking very scary, but it's not. Let me just explain the key thing here. What we said was, okay, remember that we're not interested in what the events are saying. We are just saying, when do they occur? So we say, okay, we are going to decide that two nodes are statistically dependent if they have a tendency, okay, to emit short lagged interaction more often than you expect if they were known to be random, right? So it's not a very difficult idea. It turns out that you can actually come up with a closed form formula, okay? So this thing here is just our score, which is simply saying, I'm looking at, so a Bernoulli process will have zeros and ones, and we're basically saying, the times at which I have my I node emitting a 1 and my J node emitting a 1, is that less than delta? And I just want to count that, okay? And it turns out that we can calculate two quantities here. We can predict the expected number, which means if two events have a probability of emitting some events over a period of time, what's the expected number of events that I might observe during that period of time? But even better, we can also look at the standard deviation. Okay, we can actually look at the variance around that. And even better, if you use something called a central limit theorem, you can actually show that the statistic is going to behave like a normal distribution, which is nice because it now means that we have a proper criterion to decide that when we look at the number of coincident events between two of our nodes, if there are, for example, 3 or 4 standard deviations beyond what we expect, if they were at random, we can decide that they must be statistically dependent. At least that's one way to do it. Now, of course, you might say, well, there are lots of issues here. Yes, but one thing that is very nice is we can do this very fast. Okay, and so we can actually do that very, very fast, even on very large systems. And that enables us to then formulate an inference framework. And I'm going to be quick here. I'm happy to answer after. It's not difficult, but there are two things we want to do. One is to infer a graph representation of the statistical dependencies and how these change over time. And basically so we do some assumption based on separation of timescales. And then we have windows over which we can calculate the statistic. And then we transform this statistic or this score into a probability of an edge existing. And then we have basically a dynamic to decide based on the data that we observe, what is the evolution of that probability of an edge existing over time. So here, the key things to understand is the complexity of the model is controlled by the choice of two functions, which are basically ensuring that we are having a probability despite starting from a score, which of course is unbounded. And the other thing to note is the presence of a decay, because we have to take into account the fact that the absence of information, we need to treat properly the absence of information. The absence of information could mean two things. It could mean that everything is fine, or it could mean that, well, there is no information and that's okay. Okay, so what we have is a decay which ensures that if the lack of information continues for a long time, then we lose confidence about the existence of an edge. And then the nice thing is we can actually construct an error function. And the principle is quite easy, is that from one window to the other, we basically say, look, if you had a low expectation of having a statistical edge, but you see a lot of coincidence events, then probably your probability is a bit low. And we can construct a cost like that. It turns out this function is differentiable, and we can just learn it using gradient descent. Okay, results. And the result is that there's a big elephant in this room, which I'm sure you have all realized, is you're dealing with complex systems, and you are saying, I am saying, that I'm trying to understand the relationship between the things. So my question is, where's the ground truth? How do I know that what I'm finding out is actually correct? Okay. And if there are industry-based people here, please help us with correct data, because that's probably one of the biggest problems that we have in this field, is the existence of controlled test beds for experimentation. Nevertheless, we can do a few nice things. And I'm going to start with this, which is that, remember I told you that obviously functional connectivity depends on structural connectivity. But an important thing that I tried to convey is that knowing structural connectivity cannot predict functional connectivity. And how did we go about showing this, or whether that will happen here? So what I'm showing to you here is a representation of the network following Louvain community detection, but this is not the important bit, which is colored. So the links denote the presence of statistical dependency. Okay, the color comes from information that we have about the type of events. Now, this information wasn't used in the inference program. Remember what I told you, we only use time. Okay, but what we did, we found out that in fact, most of the events produced by a single node tend to be of a particular type. So these types have been colored here. And so what we did was we looked at this community, these modules that we saw, were they all of the same type, or did they show interaction between different types? In other words, showing that there was some interaction between types of layers maybe, or services that were not expected. And so if you zoom on this, you find that you have a bit of both. So for example, you have this module here, which is very homogeneous in terms of the kind of events that it represents, right? So something might be some VMware, and that makes a lot of sense, okay? But you also have some where you have a big diversity. And now when we show that to network operators, that's a big surprise, okay? Because that is not something they will expect. That is not something they will monitor. And then, of course, the next question was, well, but could you have predicted this based on the structural connectivity? So what we did next was we kept the same representation, but now we dropped the functional connections, but show you the structural connectivity. And what you will see should be pretty obvious. It's completely different, right? So I'm going to switch again very quickly, but notice, for example, that this particular node here seems to be very central, okay? With a lot of dense connections. But if you actually look what happened to that node in terms of functional connectivity, is disconnected. So it doesn't actually seem to be playing any significant role. Okay, so I'm going to have 3 more slides. It's quick, okay? The 2 things that I've not really answered yet is, okay, so what can you do with that? Okay, it's one thing to tell we can extract some functional connectivity, but can we do something useful with it? So there are 2 scenarios I want to show you. The first one is, can we do root cause analysis? And root cause analysis is basically about providing a bit of extending what is currently a statistical dependence. And I don't need to teach this audience that correlation doesn't mean causation. So the fact that I have, a nice module here with lots of connection and statistical dependence doesn't mean that one implies the other one, right? So the intuition that we had was that, well, if you want to do the kind of, conditional testing in order to prune this mesh and actually extract some kind of directionality, what we could do is not do what people currently do, which is calculate all of the pairwise, and test extensively, which is extremely costly. What we could do was to use the information that we get from functional connectivity as a filter, okay? And because we have this modularity, it turns out that we can actually do 2 things. One is we are a lot faster, okay? Like seriously much faster. In fact, not only we are faster, but we can deal with much larger networks, okay? And the other thing, which was a bit of a surprise, but is that we don't actually drop that much information. And that was a bit surprising, but pretty robust. Okay, and then can we do anomaly detection? So this is something that we are very much working on at the moment, is to actually leverage what we have done to now say, well, can we do some kind of temporal network analysis based on this functional connectivity? Because so far, what I haven't told you is what do we do with the fact that we have inferred the time varying structure? Well, what we can do is start looking at whether changes in the structure of the functional connectivity has predictive power on some metric that occur on the network. Okay, so for example, if the networks, the structural connectivity, the functional connectivity start changing, is that possibly giving us a hint that, for example, latency is going to collapse, or that we are going to have very some kind of error? And it turns out that we have used a technique, and I'm going to skip the detail, but which enable us to basically build a distance metric between snapshots of functional connectivity. And what it showed, once you do some kind of hierarchical clustering, is that we discovered that over a period of time, for example, this network showed a very steady state in terms, even though, remember, we're dealing with temporal networks here, so the events are never exactly the same, but the fundamental structure, okay, of the relationship in this functional connectivity is actually stable over time, but occasionally shows a rapid switch. And now, obviously, this was very interesting from a complex systems viewpoint, because it could mean that you have a transition or something happening. And the next question was, well, does this actually correlate with anything, an observable that is not used in the observations that we make? And the answer, this is very preliminary, so I'm going to just say, let's call it cherry picking if you like, but at least in some of the examples, we noticed that it did seem to precede a big change in a particular metric that we had on this system. This, by the way, involved a Huawei very large-scale microservices deployment. Okay, conclusion. We are kind of trying to build a case that these modern communication networks might well be complex systems. And if they are, then it actually requires new techniques. And, well, I think we have a lot to learn from how we study the brain. One of the big things is the lack of ground truth, okay, and a need for platforms where we can, actually really explore the extent to which we predict anything meaningful. And the route that we're looking at is something called, funnily enough, chaos engineering, which is the idea of injecting fault in large-scale deployments. So something that you can do very precisely, and then we can then assess the extent to which we have predicted that, or we detect when that's going to happen. And I want to acknowledge people in my team, and I'm afraid that for this particular project, they are all men, which really upsets me, because if I were showing you other projects, they are all women. So I tried to have anyways, sorry about that. It shocks me, but I can't just put random people on the thing. And I want to acknowledge my founders as well. So Council and Movesoft. And sorry that I'm late.
Hello. Great. Thanks very much, Luke. We have time for maybe one or two questions. We might be able to come back at the end for some more. Anyone want to dive in with a question? Yeah?
It seems to me that you've got your system set up to detect a lack of information and a set of information. Which gets precedence at the moment from the data? If you've got a bad error that happens, how long does it take to? Does it quickly become apparent?
It's a really good question and a really tricky one, which I guess is synonymous. Strictly speaking, of course, we don't detect the lack of information, right? Because the only thing that we have access to are the timings of events. Indirectly, we discover the lack of information because suddenly something picks up, right? Now, the framework that we have at the moment, especially if you consider fixed times fixed windows, which we are trying to go away from, having a much finer temporal resolution, which we want to do by using something called temporal networks, is that we don't actually use that information, right? The only thing we can use is the fact that if you have had a lack of information, a particular set of nodes might be synchronous, and that might reflect the fact that that group of nodes is very sensitive to whatever caused that thing, right? Yeah, it's a very nice question. Very nice.
Thanks. And anyone else got any questions? Yeah, cool. Thanks very much, Luke. And maybe someone in the audience has some ground truth data for you. Chat to him after. Yeah, that's cool. And now we'll welcome up Minal, who is a former University of Sussex student, now studying a master's in space engineering at the University of Surrey. And Minal will be talking about utilising Astrocast for drought prediction in Marathwada. Yeah, you can use that one. Yeah.
Okay. Is this audible?
Yep.
So I'm Meenal, and like Chloe said, I'll be talking about utilizing Astrocast for drought prediction in Marathwada and hopefully in other drought-prone regions of the world. This project was supervised by Seb and Pedram at University of Sussex. And the talk will be divided in two parts. That is Astrocast. I'll talk a bit about what Astrocast is and how it works very briefly. And then Marathwada as to what it is and why we have chosen that as a region to study. Now, with Astrocast, it's basically a prediction tool that we use for prediction of droughts in Kenya. And it uses advanced data analysis techniques that were used in astronomy. Interestingly enough, this was the paper that I was using for most of my research. Now, interestingly enough, I did an astronomy project with Seb in the second year of my university. And there we were using similar data analysis techniques that were being used in Astrocast, that is autoregression or autoregressive models, where we use past data to predict future and just be able to forecast what it could look like. Now, Astrocast gives us a real-time monitoring of Kenya and allows us to predict droughts around 6 to 4 weeks before they occur, which is incredibly helpful for the government because around 80% of Kenya is semi-arid or arid, which means that they barely get any rain. And a lot of their communities depend on agriculture, cattle, and just livestock in general. And if 80% of a country is facing the situation, having something that would provide more proactive measures in helping the communities would be incredibly helpful for the economy as well, because from 2015 to around 2022, Kenya lost millions of US dollars just because of droughts in that region. And a lot of migration has to happen during droughts. People don't have enough water to live. So yeah, it's incredibly helpful. So with Astrocast, we are not just forecasting droughts, we are also providing them an early warning system for the region so that they kind of get news that, oh, it might not rain for the next couple of months and there might be droughts during that time so that people can prepare themselves. Now, this is what the Astrocast pipeline looks like. And there's many aspects to it, and I won't be going through all of it. I worked on the code for this for about a year, and after that, I was working on something completely different but related to this project. So I'll be talking more about that. But there are 4 main things that I need to talk about. And that is these 4 topics, that is MODIS and Landsat. Then normalized difference vegetation index, vegetation condition index, and forecasting. So this is NDVI and VCI, and that is what I'll be calling them throughout the talk. Now, Landsat and MODIS. There are 2 satellites in the sun synchronous orbit, so we get real-time data multiple times throughout the day for one specific region, which is helpful to have daily images of a region and understand what is exactly happening over there. Now, we use 2 satellites mostly because there is a diverse range of bands that they both provide. For this project, we mostly use near infrared and red. And it's also free to use. So why not? So these are the tiles that we kind of get in the MODIS and Landsat data. And if we were to look for Kenya in this entire map, that is where it will be approximately. Now, what we do exactly is we pick that tile. We have some like numbers over here. We choose them, pick that from the main website, put it in our code to extract the data for that region. And then we get the near infrared and red values. Now, using those values, if you put it through that formula, we get something around between 0, 1. The values kind of are in that area, and that gives us an understanding of what the plant's health is in that region. Now, for semi-arid and arid regions, it's usually dry. There's not many plants that grow. So we mostly look at grasslands. So we're looking at how dry the grass is in that region. After we get the NDVI values, we convert it into VCI values. Now, VCI is a percentile value. And now here with NDVI minimum and maximum, that is there because we get multiple values in a day as well, or over a week, over 3 months. For this project, we usually have values for 3 months. So we have VCI 3M, as you can see in the top over there. And all the values are categorized in drought, or is it extremely wet, or extreme drought. Anything below 20% is usually considered as a drought. And that's when we send a warning that, oh, there might be a drought somewhere. And yeah, so a little bit about how the data is analyzed. So we have our past data that is for let's say 3 months. And then we divide it into weekly increments. And as you can see, the spread over here is more of a forecast, and the line is what the actual data was. So for example, from 2005 to 2015, we got 10 years of data for that region. And now what we do is put it through the Astrocast pipeline. We get some values. And since it was in the past for us, since we are training the pipeline still, we have a ground reality, which is this black line over here. And this blue area is the forecasted VCI, which is pretty good. It's very useful for those regions anywhere. And this was 6 weeks before the drought occurred. So that gives enough time to prepare for water, food, just migration in general. And so I borrowed this from Seb's, my supervisor's slides. That's the map of Kenya. That's the forecast that we have. The forecast kind of looks like this. So we have color-coded the value so that people can understand. Red is always danger, and we got to move quick. So yeah, that's basically Astrocast and its pipeline in brief. If you have any questions about it, I'll answer at the end. Now going to Marathwada. this is a bit of a personal thing, so I might just wander around. So please tell me if I'm taking a lot of time. Marathwada is a place where I grew up. My parents grew up in that region, and it's in the state of Maharashtra in India. It's a very small region with 64,000 square kilometers of area, but most of the state's population lives over there, and it produces around 80% of the state's agricultural produce. Well, it used to. But the problem is, as you can see, it's near the coastal line. It should be getting a lot of rain, but it does not because it's divided by mountain ranges called Sahyadri. And because of that, the region falls into rain shadow area, where during rainy seasons, the clouds usually hit the mountains and it rains on the other side. Like it rains on the west coast, but this side usually remains dry, which also makes it a semi-arid region. And a lot of like the state population lives over there. Now, this is a news cutout from February 8th of 2024. Around 73% of the state's drought has 70. There is a 73% increase in the drought in that state, which brings down the agricultural produce of that state to around 17%, which is a huge loss for the economy because around 20% of the state's economy is now dependent on agriculture, but before this it was around 42%. Now, that's Marathwada. If we were to block it on a tile, which pretty much covers all of India, it's quite tricky to get data just specific to that region. We have shape files, which is sort of like cookie cutters, where you put that shape file on the data that we got, and it will extract the data for that region specifically. But then again, it's a very small region to get anything from. So there are a few problems that come with this. I'm not done yet, sorry. So that's basically what we are planning to do. The Marathwada is very drought prone, as I have said, and you know how the Astrocast pipeline works. The plan is to pretty much do the same thing for the same region. We could use different satellites that are specific to that region itself. India has multiple satellites which provide similar data for very small regions in the country. So that is one thing we are looking at. The other thing is setting up an early warning system. Now, early warning system, we don't have any of that in India, at least in the state. So I recently went to the Maharashtra state government in December and spoke with them about setting up this entire thing. And they have agreed on it, which is a great thing. They see something good coming out of this, which might help the people in that region. And they will be providing one person from the state government who will be coordinating with the university to work on this and provide us data. We will be speaking to farmers more and just try and understand what might be helpful for them. And since I grew up in that region, I spoke to my family about it. And they are excited to see how this might work out for that region. So yeah, it's very exciting. And yeah, it's something that the state needs a lot because from 2015 to 2022, around 15,000 farmers committed suicide, and 40% of that was due to crop failure. So this is something that is urgently needed in the state. And we are working on figuring out how we can make this happen in the most efficient way possible. But so far, it's looking good. So yeah, we have some people from the team over here. That is Chloe, who also works with the Discus. And the astronomy project I was talking about, so Maria in audience is also there. So there's a lot of people working on it. There's someone who is specifically working on the code, that is Joe. I don't remember his surname, but yeah, yeah, that's basically Astrocast. And we are hoping that we can use this for different regions across the world and yeah, be able to have more efficient early warning systems. So yeah, thank you.
Thanks. Thank you very much. And now back to the floor if anyone has any questions.
I wasn't sure if you actually said it in your speech, but how long do you think the installment of this whole process will take for your region?
Good question. So I've been working on this project for 2 years now, and we have just started talks with the government. So it might take another year or two to set up the entire system, have the code fully running, and then test it for the region. So yeah.
Got it. And one more thing, once it's set up in this region, you said setting up in multiple regions, do you think it'll be significantly quicker once you've got this test run done, as in you've got it set up in one place? Will it be quicker to set it up in others, or will it also be specific data, like you said, the cookie cutter for that region? Will you have to do that for each and every one, which will take more time?
It might take less time because while doing the test runs, we kind of realized there were a lot of things that we needed to change in the code and how we classify the data in the code as well. So yeah, I think it should be fairly quicker, but obviously not that quick. Yeah.
Excellent. Thank you very much.
Thank you.
And another question at the back.
From the information that you've got, have you tried building a playbook or an economic model to justify the use of your system?
I am working on it. So there is someone in the government in disaster management department that I'm working with to develop a proper
Yeah,
paper
because
on
that would give you a reason to do certain things if you could show that you'd save X amount of dollars.
Yeah, definitely. Yeah. Thank you.
Is there any information which you are looking at when you said that you will get a forecast 6 weeks earlier?
Mm-hmm.
So is it enough time to, have effective measures applied?
So far, yeah, because usually we get to know around a week before the droughts happen, at least in the state. And I was speaking with one of the officers at remote sensing, and he mentioned that having 6 weeks would give them enough time to have tankers to send to the villages so that people don't have to walk 2 kilometers in the sun just to get a bucket of water. They also said that it could help them kind of provide economic relief for the area and build more systems that might help with water conservation just in case it rains, because this prediction thing is something people use for floods as well and also for earthquakes in Japan. So it would be very helpful. Yeah.
Thanks. Have we got any more questions? Yeah.
I believe that in Kenya you had 15 years worth of data to make the prediction. As I understood for your region in India, you thought the process of becoming drier has been more recent. Yeah. So are you quite sure, or how have you validated that you have enough data to still be valid in terms of the prediction?
Right. So the 73% increase is this year, like we observed in the last year, but it's been a drought-prone region since 2012. So yeah, there's been a long time for us to study. Yeah. Thank you.
Any more questions? I might just sneak one in. Do you know what the kind of main type of agriculture is in this region? Like, is it a specific crop that I find it like in Kenya, it's grass, and I just wondered what the case was in.
So it's usually wheat, but not anymore. It's just grass at this point. So there is an NGO in India called Pani Foundation, which translates to Water Foundation. And I have worked with them for 4 years, just trying to build water conservation stuff in that region, as well as having sustainable farming practices. And in that, we have tried different crops, but they usually affect the pH of the soil since they're not originally from that area. So usually we are just sticking to grass so far.
Okay. Yeah. Thanks very much, Minal.
Thank you.
And thanks for everyone for coming this evening. We do have the space till 8 if you'd like to hang around, finish off the drinks, or if any of you head over to the pub. There's many to choose from in the local area. Yeah. Thanks again for coming, and keep an eye out on the Meetup page for any future events. Yeah, thanks.